Moving on to begin our study of Chapter 13, Work, Mechanical Advantage, and Simple Machines. You see levers on the screen. There are 5 more simple machines that our next set of notes will cover. Work, mechanical advantage, and simple machines are all based on forces that we talked about in the last chapter. So, as I like to say, you are not allowed to forget what you already know. You will also see a few new mathematical formulas, which means more word problems are coming. So get ready. Here we go with Chapter 13, Notes 13AB, Work and Mechanical Advantage, and Levers. Ready to begin. Work and power. Well, work is a change in position. We'll talk about power in just a little bit. An object must change position, must undergo motion in order for us to scientifically consider that work has been done. You'll see an example in a moment. Forces cause work over a distance. In fact, work equals force times distance. If there's no distance, then there's no change in position. Therefore, mathematically even, we have to say no work was performed, and we'll see why as we move along. Remember that effort does not guarantee work. We can apply a whole lot of effort, but if we do not complete a task, then scientifically speaking, no work was done. Now, many times we will put a lot of effort into something. I'm not really talking scientifically speaking here. Just put a lot of effort and get very little result. That happens, and unfortunately, things like that will happen. But scientifically speaking, if there's even a little bit of result, then we've done some work. But if you push on a wall, let's say you push on the concrete wall of this classroom, we can push and push and push. That wall is not going anywhere. Therefore, the distance is 0. Now, a moment ago, I said that work equals force times distance. Well, if the distance is 0, then we're multiplying by 0. We get an answer of, you already know this, 0. Therefore, since there is no movement of the wall on which we pushed, no work was performed. We've used up a lot of effort, we've used up a lot of energy, and we'll wear ourselves out if we try to push and push as hard as we can on that brick wall. That wall didn't move. Scientifically speaking, since there was no movement, there was no work. Ready? Calculating work. You see the pictures of the calculators on the screen, and by now you know that means a formula and some word problems are coming. Here's the formula. Work equals force times distance. And let's go back to that pushing on the wall example. Work, we use a capital W. We already know big F and little d for force and distance. We're going to figure out the work. Let's just say we put 10,000 newtons of force into pushing that wall, but we didn't move the wall, so that's 0 meters. Well, anything times 0, we already know, will be 0. And you'll see in a little bit that the unit for work is joules, just like the unit for energy, because work is energy put to use. So no matter how much force we use, if we didn't move that wall, we did 0 work, and even mathematically, that makes sense. As I like to say, math verifies common sense. We use a capital W for work. Lowercase w means weight. We know that we use a capital F for force and a lowercase d for distance because little f means something else that we'll talk about another time, frequency, and capital D means density that we studied way back at the beginning of the year. Now, let's say we moved an object. This time, we applied 20 newtons of force, a small amount of force, to move something for 5 meters. Remember, our equations, though, disregard resistant forces such as friction. Well, there you see, work equals force times distance, 20 newtons of force applied for a distance of 5 meters. Now we just multiply. 20 times 5, you already know that, is 100. And newtons times meters is called a Newton meter. Well, somebody said, well, let's not call it a Newton meter since a guy named James Joule talked about work, forces, and distances quite a bit. Let's name the unit after him. So we call the unit for work the joule, which is the same unit for energy because work is energy put to use. Even though I gave you a slightly different definition on the last screen, work is energy put to use. which causes a change in position. So the answer would be 100 joules. Now, if I know how much work is done and I need to calculate either the force or distance, remember I will already know the equals number, so an inverse operation will simply be divide. So if I know, I'm going to take that off and show you what I'm talking about. Let's say I already know that I have 100 meters here, 100 joules, I should say. And I've got 20 newtons of force, and I'm trying to figure out the distance that this object was moved. Well, since I already know the answer, I have to do an inverse operation. In this case, I'll just divide. And then D equals 5, and the unit is meters. Okay? So if we know any two of the three quantities, we can figure out the third. If we're looking for work, we're going to multiply. If we're looking for either force or distance, we will divide. Inverse operations. Ready? Now, what is power? Power in normal conversation has many different meanings, but scientifically speaking, power is how much work is done in a given amount of time. I mean, here's what I like to say for this example. I need my front yard mowed. I let one person use a push mower. Okay, self-propelled, make it easy. It will take maybe 20 to 30 minutes using the push mower to mow my yard. Someone else uses a riding lawnmower and maybe finish that job in 5 to 10 minutes. And then someone else uses a pair of scissors. Now, no matter which method the yard gets mowed, the same amount of work is done, scientifically speaking. But who did that in the fastest time? The person using the riding lawnmower, of course. So the person using the riding lawnmower will use the most power. Again, mathematically speaking, this will make sense once we get used to the formula and some problems. And again, the math verifies the common sense. Power equals work divided by time, the amount of work in a given amount of time. So perform 200 joules of work and do so in 10 seconds. How much power got exerted? All we have to do is fill in the words. Now, as I said before, and we'll keep on saying, label everything. Perform 200 joules, that's work. In 10 seconds, that's time. And we're calculating the power, that is P. Now we see which equation we have to use. You'll get to look at the formulas, but you have to pick the correct one. And then just fill in the numbers. P equals work divided by time. And now we can finish this off. Of course, you know that 200 divided by 10 is 20 joules per second. Now, somebody named Watt worked a lot with power, so the unit is named after him. Many people in science get units and other things named after them. A joule per second is called a watt. Now, we have to be talking in terms of joules and seconds in order for us to call the unit a watt. So when we see problems that say minutes, we have to convert those minutes to seconds simply by multiplying by 60 and so on. And again, if I know any two of these three numbers, I can figure out the third. In this case, if I already know power and work and I need to figure out time, I simply do a switcheroo and then a multiply or divide. If I know the power and the time, I simply do a multiply to get the work. And of course, many examples are coming. Ready? Simple machines now. How are simple machines involved in work and power? And we haven't defined yet mechanical advantage. That's coming up in a few minutes. Machines are tools or things we use to make work easier. There are 6 of them. We'll concentrate on levers this time a little bit later on in the session here. Machines can either increase the force that we put in or change the direction of the force we put in or do both. The machine, we want that machine to increase the force. That's going to make the job much easier to do. Realize, though, that machines don't change the amount of work we do, just the effort. A good machine will allow us to use less effort to get a better output and get the job done faster. So machines can help us increase the power. Machines do not change the amount of work, only the method in which we do, and therefore the time that it takes and the amount of power. So simple machines make the job easier to do. There are 6 of those. We will concentrate on lever for the rest of this session, and the next time we'll look at inclined planes, pulleys, wheel and axle, wedge, and screw. Now I want you to notice wheel and axle I put together and as one color because many people think wheel is a machine and then axle is a machine. But those two actually go together and make up one simple machine we call wheel and axle. Hopefully the colors will help you keep that straightened out. So we'll look more at levers in just a few minutes and those other 5 in our next set of notes. Ready? Now, what is mechanical advantage? What is efficiency? Here again are some fancy terms that have simple meanings. Remember the distance principle. Less effort but more distance. If I want to decrease the amount of effort force I have to put into a task, I can do that if I'm willing to apply that lesser force over a longer distance. This will come really into play in the next set of notes when we talk more about inclined planes and pulleys. The distance principle says, though, in order for me to use less effort to perform the job, I have to apply that less effort over a longer distance. Now, mechanical advantage is how much the machine magnifies the effort. And I calculate that by doing the resistant force over the effort force. Mechanical advantage is a multiplier, not a measurement. Therefore, I will not have any unit for mechanical advantage. I will have a number only. More about that is coming. There is no unit because mechanical advantage is simply a multiplier, not a measurement. How much the machine multiplies or magnifies the smaller amount of effort force we get to put in. And we'll do practice problems, of course. Efficiency is a percentage, and we already know when we calculate percentages, there's some kind of a division. So efficiency is the percentage of effort that performs the work. We will never get 100% efficiency because some of the energy we put into a task we will lose as heat, sound, or light. Therefore, we always get less output work than the effort that we put in. And that's why we're going to get a percentage when we divide, always less than 100%. You will see that as we do examples and practice problems. Ready? Now, there are 2 kinds of mechanical advantage. The first one we'll talk about is ideal. And that word ideal, remember, that means if it could happen. I'm going to adjust that and make sure you can see okay. Ideal would mean we would love for this to happen, but most likely it won't because there really are resistant forces to everything we do. With no friction, here's how we would calculate ideal mechanical advantage. The distance that we apply the effort force divided by the distance that the resistance force moves, which is usually the weight of the object supplying the resistant force. Practice problems are going to make this a lot easier to follow, but ideal mechanical advantage is the distance that we apply the effort force divided by the distance that the resistance force moves. This is unrealistic because, look at the top there again, with no friction, but there's always at least a small amount of friction. This disregards friction. Ideal would mean that would be the best possible scenario if there was no resistance. But again, there's always some kind of resistant force, and that's called friction. Ready? The actual mechanical advantage is a lot more realistic. There's always at least a little bit of friction and sometimes a lot of friction to resist what we're trying to do. Here, we're going to talk about using the forces. The actual mechanical advantage is the resistance force divided by the effort force, which means normally the resistant force is the weight of the object that we're trying to move. Remember, weight is a force. We have to apply a force in order to move that object. Now, what we want is the resistant force to be greater than the amount of effort. We want to be able to put a small amount of effort to move a large resistance. That way we get larger divided by smaller, we get a number that's greater than 1. And the bigger the mechanical advantage, the better the machine, the easier it is to do the job. Remember, on the riding mower, we really just have to press the gas pedal and the brake and turn the steering wheel once we get the lawnmower started. We get to use much less effort to do the job a lot faster. That machine will have a very high actual mechanical advantage. This is a whole lot more realistic and most likely the way we're going to get the mechanical advantage. The force of resistance divided by the force of effort. Practice problems are coming. Ready? Oh, but there is always some frictions. As you know, sometimes I forget we have an extra line on there. Now we are ready. Now, what is efficiency? Now, this one is a little bit tougher to define, but efficiency is how well a machine maintains the work input, which is the effort, and converts that effort into the work output, which is the desired result. This might sound a little confusing at first. Really, it's the output divided by the input, and the work out divided by the work in will always come out less than 100%, because we're always going to lose some of the energy put in as heat, sound, or light. Okay, try to move a heavy object, especially if we move the object over a longer distance, we're going to sweat some, so some of the energy will be left as heat and leave that system. Therefore, our efficiency is going to be under 100%. And after we divide, we get a decimal. We simply change a decimal to a percent by moving that decimal point 2 places to the right. You already know, but it's easy to overlook. The higher the efficiency, the better the machine. So we want machines with high efficiency and high mechanical advantage. Those two quantities mean the machine makes our work much easier to do. And unless we're trying to do something like strengthen our body and our muscles, why would we want to use a machine that makes the work harder to do? Now, lifting weights, we want higher resistance and less effort because that's what strengthens our bodies. But then again, that's the purpose of lifting weights. If we're trying to get a job done as easily as possible, why would we choose a machine with less mechanical advantage? We want a high mechanical advantage and a high efficiency. But remember, efficiency is always going to be less than 100% because there's always at least a small amount of effort lost as heat, sound, or light. That should make sense. Ready? Now, let's look at levers, the first of the 6 simple machines. In our next session, we'll talk about the other 5. There are actually 3 kinds of levers. And there you see on the right, you see a guy pulling on a lever that may be connected to a conveyor belt. And you see the kids on a seesaw at the bottom. Okay. Here's your definition of a lever. A bar turning on a fixed point, and that fixed point is called the fulcrum. Okay, I'll come over here. And on the seesaw, this is actually easier to show. The fulcrum would be right here. That's where the pivot point is. And we can use a capital F to indicate fulcrum. Now this guy, the lever goes into the floor, so the fulcrum may actually be down here a little bit under the floor, so we can't really see that in the picture. And maybe there's a conveyor belt right here. He has a heavy object that he's trying to move in that direction. And in case that didn't come out well, he's trying to move that to the right across our screen. Rather than carry that heavy box, he's going to pull on this lever and cause these gears, which are wheels, other simple machines, to turn and move that conveyor belt and pull that object all the way across to the other side of the system. Levers are bars that turn on a fixed point, and we call that fixed point a fulcrum. In the Old Testament, people used levers such as a scale, which is kind of like a seesaw, to try to measure out and see how much the silver and gold is worth. You think there were cheaters back then? Oh yeah, just like we have now. Some people try to cheat other people. Well, of course, the Bible says don't do that. Proverbs 11:1 warns us about false measurements, which is cheating and lying, and in that case, stealing. Of course, all of those break the 10 Commandments. So Proverbs 11:1 tells us use the levers for good purposes, not to cheat other people. Ready? Law of moments is actually another formula that we're going to work, and that has a second name as well, law of torques. And even in the same textbooks, you might see both of those terms used. Torque is force in a circular direction. So watch this kid here. If he was to go down, he would not actually go straight down. He would actually go more of a circular kind of down. And if this were to continue, we would get, pretend I draw well, we would eventually get a complete circle. Okay, watch this. Okay, I got my stick here. This is torque, a force applied in a circular direction. Okay. And that's what happens on the seesaw. This shows conservation of work. So we have another law of conservation. Work cannot be created or destroyed, only changed in the method performed. The work we do is the same regardless of which method, and again, mathematically, that works out. As you'll see, maybe not this time, but you will in the next set of notes. And this shows that we want a balanced lever. Okay, balanced levers make the machines work and function a lot better. Unbalanced, where something's wrong with the lever, could mean something's wrong with the machine, and then we don't get the desired results. Okay, now, for example, 250 newtons sitting 2 meters away from the fulcrum is equal to 100 newtons sitting 5 meters away from the fulcrum. Let's just say this. This guy here weighs 250 newtons, although the picture isn't really drawn to scale. He's sitting 2 meters away from the fulcrum right there. Now this isn't balanced. We're going to assume that it is and be straight across. This kid here, if he weighs 100 newtons, he can sit 5 meters away. So it would be a little more like this if I put it here. This would be 2 meters. Let's make that a little more realistic. 5 meters here, okay? And 250 newtons and 100 newtons here. Now let's multiply. 250 times 2, well, that's 500. So that would be 500 joules of torque. 100 times 5, that would be 500 joules of torque. So in this case, we could balance the seesaw by having 2 different weights sit in the correctly proportioned distances away from the fulcrum, which would be the pivot point right there on the seesaw. 500 joules equals 500 joules. We have the same amount of torque on both sides. Lab activities that we will do soon, we'll be able to practice this for real, not just see numbers and pictures on a screen. But that's the law of moments, or the law of torques. And although it doesn't show on this page here, let's write it. The force and the distances on one side are equal to the force times the distance on the other side. F1 D1 equals F2 D2. Ready? The law of torques. See the 2 kids on the seesaw here. How far from the fulcrum of a seesaw would a 300 Newton girl sit to balance a 400 Newton boy sitting 3 meters from the fulcrum? That's not 300 pounds and 400 pounds. That's newtons. Divide by 4.44, you'll see those are much more reasonable weights. Okay, now let's do the math here. I gave you this a few minutes ago, just a couple moments. F1, D1. Now, it doesn't have to be 1s and 2s. It can be left side, so L's and R's, or it could be girl and boy. Doesn't really matter. Now, let's fill in the numbers. We have a 300 Newton girl on one side and a 400 Newton boy on the other side. So 300 Newtons here and 400 Newtons here. The 400 Newton boy is sitting 3 meters, so that's D2. This is F2, this is F1, and we're looking for D2. He's sitting 3 meters away. Let's just do the math. All right, 300 times D1 equals 400 times 3 is 1200. And since that's torque, that's joules. And simply divide by 300 now. 1,200 joules divided by 300, assuming I didn't make any mistake, 4 meters. Since that's a distance, that has to be meters. Now, assuming I didn't make a goof, here we go. 400 newtons times 3 meters equals 300 newtons times the distance of the boy on the right side. 1,200 newton meters equals 300 newtons times D2, and there we go. 4 meters equals D2. So the boy would have to sit 4 meters away from the fulcrum, which would be here, in order for this to be straight across and balanced. Ready? Of course, practice problems are coming. Now, in a lever, we have 3 kinds. So as far as what to write, here's what you need to write here. Write first class levers, effort, fulcrum, resistance. Notice that the fulcrum is always in the middle. This is your definition of a first class lever. You don't have to draw the pictures, but know that in a first class lever, write this down. Effort, fulcrum, resistance. Keep in mind though, we can put this backwards. In fact, I'm going to go ahead and do that on the screen here. Get a color that will show up better here. We could also have resistance, fulcrum, and effort as long as fulcrum is in the middle. We have a first class lever. Now the fulcrum doesn't have to be exactly halfway. It could be further over here or further over here. As long as the fulcrum is in between effort and resistance, we have a first class lever. So again, this is what you want to know. And it could be RFE. In fact, all 3 classes could be reversed from what you see on the screen. First class lever, effort, fulcrum, resistance, as long as F is in the middle, first class. Ready? In a second class lever, here again, write this down. And put that over here now so I can reach better. Remember that we could also have, as long as R is in the middle, ERF. Second class lever, the resistance is in the middle. Now look at the wheelbarrow. We would push up here to be able to dump the dirt out. The fulcrum is right here. That's our resistant force, and our effort force is here. We're going to dump this. Now, a few minutes ago, you saw the term distance principle on the screen here. If I have a longer handle, remember, I get to apply less force, but over a longer distance. That will make, let's do that again. If I have the longer handles, that will make my effort a lot easier because longer distance, greater distance right there. I still have the fulcrum, I still have the resistance. A longer handle on the lever, in a second class especially, that is going to allow us to dump that wheelbarrow out a lot more easily because we get to use less effort, because that effort is magnified or multiplied along every segment that we can think of on that effort arm. Okay? Now, let me back up because I forgot to tell you something. The crowbar represents a first class lever. Okay. With the fulcrum right here, we're going to apply the effort here and pull back sort of a circular. And whatever's attached here, like we're trying to pry a nail out of a board or pry 2 boards apart, that's your resistance. And again, the longer the effort arm, the easier it is to use that machine. Less effort over a longer distance. If we tried to pull here, that's going to be harder to do. So I'll make that dotted. But if we pull out toward the end, that's going to be easier to do. Lab activities coming up will show that. Okay, and I showed you the second class. Now look at the third class lever. You have the guy using a mop right there. Yeah. Maybe this color here. His effort, he's putting right there in the middle here. That may not work, so let me get a better color here. Right there where his hand is. The fulcrum is here. He's kind of turning. Here you go. He's kind of turning like this at the top, and he's pushing and pulling just underneath. And where the mop scrubs against the floor, that's the resistant force. So put the resistance down here. Effort in the middle. So for third class, effort is in the middle. And remember, it could be reversed. We could have those three backwards. This is what matters. The middle part of the lever determines which class. Fulcrum in the middle, first. Resistance in the middle, second. Effort in the middle, third. And again, it doesn't have to be halfway. As long as effort is somewhere in between resistance and fulcrum, we have a third class lever. So his scraping the mop across the floor back and forth, that's going to provide the resistance. There's a turning point there, and he's pulling right there. Okay, so third class lever. Think of a baseball bat as well. Okay, it would be a lot easier to show you in class, but we don't have really much space up here to do that. But there you go with your three classes of levers. Ready? And that is all. The end. Work to achieve. Now, next time we'll talk about the other 5 simple machines and how mechanical advantage and efficiency apply to them to make work easier to do. Thank you.